So let's extend these Lewis structures a little more and start talking about VSEPR theory. VSEPR theory explains why molecules take the three-dimensional shape that they do. And while this is not my HL biology course, you should know that when we talk about variants in the news, very often what we're describing is changes in the shape of the S protein, the spike protein, that make the virus more or less capable to infect our cells. But let's look at two much more simple compounds, water and carbon dioxide. Water and carbon dioxide are both pretty similar in size, being made up of only 3 atoms, all of which are nonmetals, yet their properties are wildly different. You learned last year in biology that water is responsible for many of the properties of life because water is a polar molecule. But what you didn't know is the reason water is polar is not because of the atoms it's made up of, but because of the shape that water takes. It's this bent shape that gives water the polar properties that sustain life. And since carbon dioxide is not bent, it is not polar. Predicting the three-dimensional shape of these simple molecules is actually quite easy if you know something called valence shell electron pair repulsion theory, also called VSEPR. VSEPR theory states that it's the valence shell only that determines the shape of a molecule. And it's because this valence shell holds the electrons that are involved in the bonding of that molecule and also any non-bonding lone pair electrons. If we recall that all electrons have a negative charge, then it's easy to know why the valence shell electrons, whether they're bonded or lone pairs, will repel each other. And molecules will adopt a shape to minimize this repulsion, basically making these electron zones, these valence shell electron zones, as far away from each other as possible. By knowing the number of bonded electron zones as well as the number of lone pair electron zones around the central atom, that's the important one, around the central atom, it allows us to predict the shape of these molecules pretty accurately. So let's look at an example of CO2 and water and how we would get to the straight shape or linear versus the bent shape. First, identify the central atom in the molecule. In CO2, it's the carbon, and in the water, it's the oxygen. Then identify all the electron zones around the central atom. Those can be lone pair zones or they could be bonded zones. In CO2, the carbon has 2 zones surrounding it, while in water, the oxygen has 4 zones surrounding it. In the carbon dioxide, all of those zones are bonded zones and none of them are lone pair zones. Where when we look at water, the 4 zones, well, 2 of them are bonded and 2 of them are lone pairs. Once we've identified the total number of zones and which of those zones are bonded versus lone pair, then we just got to look at this handy little reference sheet that is in your reference packet. The numbers across the top of the reference packet are the total number of electron zones in the molecule around the central atom. Central atom. This is also called the electron geometry, which I'll explain that word in a moment. The numbers to the left side of the table represent how many of those total zones are lone pair electron zones. So if we were to look at carbon dioxide specifically, we know that there are 2 total electron zones around the central carbon, and both of those electron zones are bonded zones. So that means there are 0 lone pair electron zones. Using this information, we could read the table and see that the shape of a carbon dioxide would be linear. Linear meaning the molecule makes a straight line in space, and that the angles of the 2 bonded atoms, they're 180 degrees away from each other. When we use the chart for water, however, we can see that there are 4 total electron zones, and of those 4 electron zones, 2 are lone pair electron zones. This is how we arrive at the bent shape for water. Lastly, let's look at 3 very similar molecules to explain the difference between molecular geometry and electron geometry. If we look at these 3 molecules' Lewis structures, we see that they each have 4 total electron zones. But by looking at where those electron zones are bonded to other atoms, we can see where the difference lies. All 4 have 4 electron zones, so all 4 have what is called tetrahedral electron geometry. But it's not where the electrons are that describe the molecule, it's where the atoms are. And so even though all three molecules have 4 electron zones, they have a different number of bonded zones. Therefore, their molecular geometry is different. CH4 has 0 lone pairs, therefore its molecular geometry is tetrahedral. NH3 has 1 lone pair, so its molecular geometry is trigonal pyramid. And H2O has 2 lone pairs, so its molecular geometry is bent. Again, the electron geometry for all of them is tetrahedral because they all have 4 electron zones. But the molecular geometries are different because not all of those zones are bonded zones. CH4 has 4 bonded zones, NH3 has 3 bonded zones, and H2O has 2.